In the pitch-black cold of the Pacific Ocean floor, nearly 300 miles off the coast of Oregon, something massive is breathing. It is not a creature, but a geological titan that has remained relatively quiet for almost a decade. This is Axial Seamount, the most active submarine volcano in the Northeast Pacific, and right now, the instruments placed there by scientists are screaming. The internal pressure of this underwater giant is surging at a rate that has caught the global scientific community off guard. We are talking about a literal mountain on the seafloor that is inflating like a balloon, stretching the crust of the Earth to its absolute limit. If you thought volcanic threats were only a concern for places like Iceland or Hawaii, you need to look deeper, much deeper. Something is happening at the bottom of the ocean that could rewrite our understanding of how our planet functions. And the countdown to the next major magmatic event has officially entered a critical phase. To understand why people are getting so nervous about Axial Seamount, you first have to visualize where it is. It sits on the Juan de Fuca Ridge, a place where the tectonic plates are pulling apart, allowing molten rock from deep within the Earth to rise toward the surface. Most underwater volcanoes are difficult to study because they are isolated and silent. But Axial Seamount is different. It is wired. It is part of the Ocean Observatory's Initiative's Regional Cabled Array, which is essentially a massive extension cord running from the Oregon shore all the way out to the volcano. This cable powers a network of high-tech sensors, seismometers, and pressure gauges that send real-time data back to shore at the speed of light. Because of this, scientists aren't just guessing about what's happening. They are watching the volcano's heartbeat in real time. And lately that heartbeat has been racing. The most shocking metric coming off the seafloor right now is the vertical inflation. Imagine the seafloor actually rising by several inches every single month. This happens because magma is injecting itself into a chamber just beneath the caldera floor. As the chamber fills, the ground above it has nowhere to go but up. Since its last major eruption in 2015, Axial has been recharging. But the recent acceleration in pressure is far beyond the normal background levels. For the first time in years, the inflation has reached a threshold that historically precedes a massive release of energy. When the pressure gets this high, the rocks surrounding the magma chamber start to crack. We are seeing thousands of tiny earthquakes every week, tectonic whispers that a major movement of molten rock is imminent. But let's talk about why an underwater eruption is so scientifically fascinating compared to one on land. On land, a volcano releases gases into the atmosphere and sends ash into the sky. Underwater, at the depths of Axial Seamount, the sheer weight of the ocean above the hydrostatic pressure keeps the gases dissolved in the lava. Instead of a massive explosion of ash, you get something called pillow lavas or lobate flows that crawl across the seafloor. However, these events still release an incredible amount of heat. During the 2015 event, the water temperature in certain areas spiked so high it created underwater weather systems. With plumes of warm, scientists are now watching for the first signs of these thermal plumes, which would indicate that the crust has finally snapped. The surge in pressure at Axial Seamount isn't just a local Oregon problem, it's a window into the very engine of our planet. By studying how the seafloor inflates and deflates, researchers are learning how magma moves through the Earth's crust. This is data they can't get easily on land, because the thick continental crust obscures the view. At Axial, the crust is thin, allowing for a much cleaner look at the magmatic plumbing. The current pressure surge is giving them a textbook example of inflation-predictable behavior. Basically, Axial has a habit of erupting once it reaches a certain height or pressure level. We are currently approaching that glass ceiling. The good news is that Axial Seamount is deep, about 1,400 meters below the surface. An eruption there doesn't typically trigger tsunamis because the movements are mostly horizontal lava flows rather than massive vertical displacements of the entire seafloor. However, the biological impact is immense. These seafloor volcanoes are home to extremophiles, creatures that live in total darkness and survive on chemical energy from the volcano rather than sunlight. When a pressure surge leads to an eruption, it creates entirely new habitats. It's a cycle of destruction and rebirth that happens in one of the most hostile environments on Earth. Scientists are eager to see if a new eruption will wipe out existing colonies of tube worms and bacteria, only for new life to emerge from the cooling rock within days. But the real mystery lies in the why of this current surge. Why now? Why is the pressure increasing faster than it did in the lead-up to the 2011 or 2015 events? Some researchers suggest that the mantle source feeding the volcano has become more active, or that the internal plumbing of the ridge has shifted, allowing magma to flow more easily into the shallow chamber. This is the cutting edge of geophysics. Every time the pressure ticks up, we are getting a look at the pulse of a mid-ocean ridge. To give you an idea of the scale of this monitoring effort, the cabled array at Axial Seamount is one of the most complex engineering feats in the history of oceanography. There are hydrophones that act as underwater microphones, catching the sound of the crust cracking. There are tilt meters that can detect a change in slope equivalent to the thickness of a human hair over a mile. When the data showed the recent surge, the laboratories at the University of Washington and Oregon State University went into high alert. They are now using machine learning algorithms to sift through the thousands of micro-earthquakes, trying to find the specific signature that signals the magma is finally breaking through to the surface. What makes this specific pressure surge so captivating is the predictability or lack thereof. While Axial has followed a pattern, volcanoes are notoriously fickle. They can inflate to a certain point, and then simply level off, as if the magma found a different place to hide. But the current trend line for Axial is steep. It's not leveling off, it's accelerating. If the trajectory continues, many experts believe we could see a significant magmatic event within a very short window of time. This would be the first time in history we have been able to watch every single second of a major seafloor eruption from the very first crack to the final cooling of the lava. Let's dive a bit deeper into the seamount itself. Axial isn't just a bump on the bottom of the ocean. It's a massive feature that stands at the intersection of a mid-ocean ridge and a hotspot, the same kind of geological feature that created Hawaii. This double whammy of magma sources is why Axial is so much more active than its neighbors. It's like having two separate pipes filling the same tank. When the pressure surges, it's a sign that both of those pipes are wide open. This makes it a perfect laboratory for understanding hotspot-ridge interaction, a process that has shaped many of the world's ocean basins over millions of years. The data streaming from the seafloor also reveals something called long-period earthquakes. These are low-frequency rumbles that sound like a giant pipe organ being played deep underground. They are caused by the resonance of magma moving through conduits. In the last few months, these long-period events have become more frequent at Axial. It's as if the volcano is humming to itself as it prepares for its next big move. For seismologists, this is the holy grail of data. Being able to hear the magma move provides a 3D map of the volcano's interior without ever having to drill a hole. But it's not just about the lava. The pressure surge is also affecting the hydrothermal vent systems. These are black smokers, chimneys that belch out superheated water filled with minerals like gold, copper, and zinc. The plumbing of these vents gets squeezed. We are seeing changes in the chemistry and temperature of the fluids coming out of these vents. For biologists, this is a warning sign. The animals living around these vents, limpets, crabs, and strange scale worms, are extremely sensitive to these changes. A surge in pressure could mean their world is about to be paved over by fresh basalt, forcing them to find a new home in the dark. One of the most exciting tools being used to monitor this pressure surge is the self-calibrating pressure recorder. And even a tiny change in the height of the seafloor can be masked by the changing tides and ocean currents. These new sensors are so precise they can filter out the noise of the entire Pacific Ocean to see the tiny millimeter-scale movements of the volcano. When these sensors started showing a consistent, upward trend that deviated from the normal tidal cycles, that's when the awakening narrative really took hold. Axial isn't just sitting there. It is actively pushing back against the weight of the ocean. As we look at the potential scenarios for the coming months, there is a sense of watchful waiting. Unlike a volcano on land, where you might see steam or smell sulfur, seafloor volcanoes are hidden by miles of water. We rely entirely on our robotic proxies, but those proxies are telling a clear story. The magma budget, the amount of molten rock entering the system versus the amount leaving, is currently in a massive surplus. This surplus has to go somewhere. Usually it ends in a dike injection, where a wall of magma thrusts itself horizontally through the crust, often breaking the surface to create a brand new layer of seafloor. The scientific community is also using this pressure surge to test new theories about volcanic forecasting. If we can successfully predict the exact day Axial erupts based on these pressure readings, It would be a massive leap forward for volcanic safety everywhere. While Axial doesn't threaten cities, the principles are the same for volcanoes that do. If we can master the inflation-to-eruption ratio at a controlled site like Axial, we can apply those lessons to places like the Bay of Naples in Italy, or the Cascades in the Pacific Northwest. Axial is essentially our Rosetta Stone for understanding the language of magma. There's also an element of extreme engineering involved in this story. The cables and sensors at Axial have to survive in a high-pressure, corrosive environment. When the volcano eventually does erupt, it might destroy some of the very instruments watching it. During the 2015 event, several sensors were actually buried under fresh lava flows. But even their final messages were valuable, providing data on the exact temperature and speed of the advancing lava. Scientists are prepared for this. They see the potential loss of equipment as a small price to pay for the ultimate dataset. What's truly mind-blowing is the sheer volume of rock we are talking about. During a typical Axial event, enough lava is produced to pave a standard 2-lane highway from New York to Los Angeles. And all of this happens in total silence. Hidden from the human eye, under the crushing weight of the sea, the current pressure surge suggests that the next event could be even larger. We are seeing a buildup of potential energy that has been accumulating for 9 years. The crust is like a rubber band that has been stretched to its limit. When it snaps, the release will be magnificent. The recent flurry of activity also brings up questions about the broader tectonic health of the West Coast. Axial Seamount sits on the Juan de Fuca Plate, the same plate that is being pushed under the North American continent at the Cascadia subduction zone. While an eruption at Axial is a separate volcanic process from a subduction zone earthquake, they are all part of the same massive conveyor belt of tectonic activity. Monitoring the output at Axial helps scientists understand the overall input of the tectonic system. It's like checking the pressure in one part of a complex hydraulic system to see how the whole machine is doing. For those of us watching from the shore, the updates from Axial Seamount are a reminder of how dynamic our planet truly is. We often think of the seafloor as a static, finished place, the basement of the world, but it's actually a vast, ever-changing construction site. Fresh crust is being born at Axial every few years, expanding the seafloor, and literally pushing the world apart. The current pressure surge is just the latest shift in that construction project. It's a reminder that beneath the waves there is a world of fire and pressure that is just as intense as anything we see on land. As the inflation continues to climb, the team at the Ocean Observatory's initiative is increasing the frequency of their health checks on the remote instruments. They are looking for seismic swarms, hundreds of earthquakes happening in a matter of hours. This is the classic precursor to a breakout. Autonomous underwater vehicles, AUVs, are being prepared for deployment. These robotic sharks will be sent to the seamount to take water samples and high-resolution photos of the seafloor once the all-clear is given. They are looking for glassy new lava, which looks like black obsidian, reflecting the lights of the robots. The beauty of recent discoveries at Axial is not just in the data, but in the accessibility. Because the data is public, students and amateur scientists around the world can watch the same pressure charts as the professionals. You can literally go online and see the seafloor rising in Oregon in real time. This level of transparency has turned Axial into a public volcano, a shared scientific experience that connects people to the deep ocean in a way that was impossible just 20 years ago. Let's talk about the biological renaissance that happens after these pressure surges. Deep-sea vents are often called islands of life. When a volcano erupts, it can create megaplumes, massive bubbles of warm water that can carry larvae and nutrients for hundreds of miles. This helps seed other parts of the ocean with life. The surge we are seeing now could be the start of a biological export event that will affect the ecosystem of the entire Northeast Pacific. It's a reminder that even the most violent geological events have a role to play in the flourishing of life. The current situation at Axial Seamount is a masterclass in modern Earth science. It combines satellite telemetry, deep-sea robotics, fiber optic communication, and advanced geophysics to solve a puzzle that has been hidden for billions of years. We are no longer just reacting to the Earth's movements. We are anticipating them. The pressure is surging, the ground is rising, and the deep-sea sensors are ready. Whatever happens next at Axial Seamount, it will be a spectacle of nature that we are privileged to witness with unprecedented clarity. When the magma finally breaks through, it won't be a disaster, but a celebration of discovery. For the scientists who have spent their careers watching this specific patch of the seafloor, it will be the culmination of years of hard work. They will see their models tested and their theories refined. And for the rest of us, it's a chance to marvel at the sheer power of the world we live on. The Oregon seafloor has awakened, and it has a story to tell that is written in the language of pressure and heat. As we continue to monitor the surge, we have to appreciate the delicate balance of the systems involved. The magma chamber is a finely tuned engine. If the pressure isn't high enough, the magma stays put. If it's too high, the crust yields. Right now, we are in that tense middle ground, the overpressure phase where anything can happen. It's like watching a balloon being blown up to its maximum size. You know it's going to pop. You just don't know which specific breath will be the last one it can take. The excitement in the scientific community is palpable. This isn't just about one volcano. It's about the future of how we live with all geological hazards. By understanding the tipping point of an underwater seamount, we gain universal knowledge about the strength of Earth's crust and the behavior of fluids under extreme conditions. The pressure surge at Axial is a laboratory experiment conducted by the Earth itself, and we have the front row seats. The story of Axial Seamount is also a story of human persistence. It took decades to build the infrastructure necessary to monitor this site. It took the collaboration of multiple governments, universities, and private organizations. Every time the pressure sensor sends a new reading, it is a victory for human ingenuity. We have successfully extended our senses into one of the most inaccessible places on the planet. And what we are hearing is a clear message. The Earth is alive. It is changing, and it is far from finished. As the pressure continues to build off the coast of Oregon, we remain in a state of high-tech anticipation. The seafloor giant is stirring, and its internal clock is ticking toward a spectacular finale. We will be watching every vibration and every tilt, waiting for the moment when the Pacific floor opens up to reveal the fiery heart of our planet once again. This is science at its most raw and exciting. A real-time look at the creation of our world, one pressure surge at a time. There is also a profound sense of scale here that is easy to lose. When we say the seafloor is inflating, we aren't just talking about a small patch of dirt. The caldera of Axial Seamount is about 5 miles wide and 8 miles long. That entire area is moving. The sheer energy required to lift that much rock against the weight of the ocean is staggering. It's a testament to the incredible power stored within the Earth's mantle. The pressure surge is just a tiny symptom of a planetary engine that has been running for 4 billion years. As we move forward, the data from Axial will continue to be integrated into global climate and geological models. Even underwater eruptions contribute to the ocean's nutrient cycles and carbon sequestration processes. Nothing in the Earth's system happens in a vacuum. The surge and pressure at a remote seamount in the Pacific has ripples that extend through the water column and into our broader understanding of the planet's health. It is all connected, from the smallest tube worm to the largest magmatic plume. The awakening of Axial Seamount is more than just a headline. It is a live-action thriller playing out in the deep sea. It has intrigue, high-tech gadgets, ancient forces, and a mystery that only time and pressure can solve. We are currently in the most exciting part of the story, where the tension is at its max, and the resolution is just around the corner. So keep an eye on those seafloor charts. The next update could be the big one, the moment the Oregon seafloor officially makes its presence known to the world once again. In the end, Axial Seamount teaches us humility. For all our technology and all our understanding, we are still just observers of a much larger process. We can measure the pressure, we can hear the cracks, and we can predict the event, but we cannot stop it. We are simply guests on a restless, beautiful, and powerful planet that is constantly recreating itself. The awakening of the seamount is a reminder of that power, and a call to continue our quest for knowledge in the vast, unexplored reaches of our ocean world. The pressure is on, literally, and we wouldn't want to be anywhere else. The team on the ground, or rather the team on the shore, remains vigilant. They are checking the data streams every few hours, looking for that one telltale sign that the surge has reached its peak. The excitement is tempered by a deep respect for the forces at play. This is geology in real time. This is the pulse of the Earth. And as long as Axial Seamount is breathing, we will be there to listen. The awakening is here, the pressure is surging, and the deep sea mystery is about to be revealed. Stay tuned, because the bottom of the ocean is about to get very, very hot.